To wrap up our discussion on the wave model of light, we want to look at polarization. So experimental evidence that we've kind of had for light being a wave had to deal with Young's double slit experiment, which was kind of a consequence of Hawkins' principle. And then we also talked about kind of the Poisson bright spot that also gave evidence for the wave model. But of course, people were always demanding more and more and more evidence to satisfy their lust for, scientific progress. So the last little bit of evidence that we could kind of supply to show that light behaved as a wave had to deal with polarization. And this came about because when we talked about waves in Physics 20, we talked about the case of longitudinal waves versus transverse waves. So to refresh, longitudinal waves are those waves that have their energy disturbance in the same direction as the traveling of the pulse. Whereas for a transverse wave, we have that energy disturbance that's going to be perpendicular to the direction of our pulse travel. So the first thing is we had to kind of figure out what type of wave is it? Is it transverse? Is it longitudinal? So to answer that, we are going to look at this polarizing filter. Now, here's a transverse wave, so we can kind of see that this is our direction of motion to the right here, I guess we'll say, or we could say left, it doesn't really matter, but it's in this kind of horizontal plane, whereas our disturbance is in this vertical plane. Now, if I pass this wave, this vertical oscillating wave through this vertical filter, it's going to get through no problem. But if it gets to this horizontal filter here, well, there's going to be no light passing through here, so that's going to block out the light. If light was to behave as a longitudinal wave, well, the oscillation's kind of going back and forth, not in a vertical nor horizontal plane. They're not going to be affected by vertical or horizontal polarizers. In fact, light will pass through. So what we had to do is we had to do a little bit of a test. We had to take two polarizers with their transmission axes at 90 degrees to one another, and we had to check, did light pass through it or did light not pass through it? Now those of you that have played around with polarizers or worn polarizing sunglasses, you'll know that if you tilt the polarizers at the right angles relative to one another, you will start to get a darkening. So what we've actually found is that if we do have light traveling on polarizing filters that are at 90 degrees to one another, we are not going to be able to have light pass through it. What that tells us is that light is a transverse wave and it's not longitudinal. So all of that stuff we've done on electromagnetic theory or electromagnetic waves, we're dealing with transverse waves strictly. So as I mentioned, this object here, this is what we call a polarizing filter. The whole job of a polarizing filter is only to allow one oscillating plane of light through, or restrict light to one oscillating plane. So what I'm going to show you is kind of more with this diagram here. So if we have a light source, it's going to be what we call unpolarized. What that means is the light is going to oscillate in all possible directions. So we kind of see all the oscillatory planes. So what a polarizer is going to do is it's only going to allow through one specific plane of polarization. So if we have this vertical polarizer here, all it's going to do is it's only going to allow light that is in the vertical plane. Everything else gets rejected. So when the light approaches this filter, only our vertical bits of light are going to pass through. So we'd say that the light is vertically polarized. Now, if I happen to take that vertically polarized light and pass it on a horizontal polarizer, well, this light being perpendicular to this transmission axis, nothing is going to pass through. We're going to be able to block the light on this. And polarizers are something like, if you wear sunglasses that are polarized, the gist of those is you want to block out a little bit of the light. You don't want to block out all the light because you still want to see what's in front of you. But those of you who have worn polarizing sunglasses and tried to look at like a computer screen or your phone or something to that effect, those screens are also polarized. So if you're looking at them at the wrong angle, you'll notice it's really hard to see the screen because what's happening is kind of something like this. The light that's coming from that screen is polarized in one plane. Your glasses are polarized in a different plane, so you're blocking out a lot of light. That's one of the issues of trying to wear polarized sunglasses and read computer screens. It's not the most effective. So you'll see people trying to tilt their head to rotate that transmission axis. And yeah, polarization of light, it's important just because it highlights again that light behaves like a wave. If it was a particle, it'd get through a polarizer no problem. So polarization supports the idea that light behaves as a wave, specifically that it behaves as a transverse wave. And it also supports the concept of light being composed of perpendicular oscillating electric and magnetic fields, with the direction of propagation being perpendicular to those two fields. So polarization, as we mentioned, it's used more significantly for glasses and all that, because again, we don't want all that UV radiation, all that light on our eyes. We would certainly like to reduce the intensity of that just so we don't hurt our eyes. So this covers the wave model of light. What we're going to start to transition into next is we're going to start to look at the particle model of light, look at evidence for it, and then kind of see that tension that comes up between the wave model and the particle model. So stay tuned for that.